Any process for the fabrication of aluminium components determines not only the shape of the component, but also its microstructure. In turn, the microstructure determines the component's attributes. It is very important to understand the interaction between processing chain, component shape, microstructure, and the component's properties is very important. Aluminium has a face-centered cubic lattice structure. This means the atoms are arranged so that they form the corners of a cube, with one atom in the center of each face. The length of a side is about 0.4 nanometer. If the material is strained enough to cause plastic deformation, certain crystal planes slip in particular directions. This figure presents a schematic illustration of an imperfect crystal structure. Certain planes of atoms end in the middle of the crystal. The line that forms along the edge of such an extra plane is called a dislocation. The dislocations move along the slip planes. This figure illustrates a cold metal process called cold forging or impact extrusion. A cylindrical blank is cut from an extruded rod. When it is subjected to plastic deformation during the extrusion operation, dislocation sources will be formed inside each grain under the influence of external forces. The metal is strengthened by the deformations. When sufficiently heavy deformations occur, it will reach a state of equilibrium between the formation of new dislocations and the annihilation of old ones. Thus, the work hardening has reached the saturation point. The curve will flatten out as indicated in this figure. Heating will cause a component's locked locations to melt together and disappear, annealing. We will obtain a recovered structure with a lower strength. It is possible to achieve the desired combination of strength and ductility through a controlled heating process called partial annealing or back annealing. When atoms from another metal replace aluminium atoms in a crystal lattice, it is called that the alloying element is in solid solution. Manganese and magnesium are typical examples of alloying elements in solution in aluminium. These atoms do not quite fit into the lattice, meaning the surrounding aluminium atoms are displaced slightly. This impedes the migration of dislocations through the crystal. This figure shows particles, or thin bars, precipitated in the crystal lattice. Such particles are formed when alloying elements in solution are oversaturated, solution heat treatment, and precipitated, aging. Solution heat treatment can take place when the amount of the alloying elements in solution is reduced in proportion to temperature. We can see this from the phase diagram for the aluminium-magnesium-silicon system. The figure shows a cross-section of the diagram based on percentage weight of magnesium-silicon phase along the horizontal axis. In the alpha phase area, magnesium-silicon phase are in solid solution. When an alloy containing approximately 1% of magnesium-silicon particles is quenched rapidly from a temperature of about 570 degrees Celsius to room temperature, the alloying elements will not have time to diffuse and form particles. The aluminium metal becomes oversaturated with magnesium and silicon in solid solution. Artificial aging involves heating the alloy to roughly 180 degrees Celsius for a few hours. This will facilitate a controlled diffusion, migration, of the dissolved silicon and magnesium atoms towards the areas where the intermetallic magnesium-silicon phase begins to precipitate. At the same time, the surrounding crystal lattice will be slightly deformed because the precipitates do not quite fit into the structure. The hard needles precipitated, combined with the deformation of the surrounding lattice structure, mean that considerable external forces are required for a dislocation to pass through such areas. Consequently, the material's flow stress increases significantly. If the alloy is kept at this high temperature for too long, it has been overaged, and the flow stress declines again. When the metal solidifies, the solidification process begins with small, solid particles in the melt. These particles grow into crystals shaped like a dendrite. Each dendrite grows until it encounters neighboring grains. The metal between the arms has a different composition of alloying elements and impurities. This process forms an alloy's cast structure. Wrought alloys are hot rolled or extruded after being cast and homogenized. The cast structure will then be broken up and a new grain structure will be formed by recrystallization. The combination of cold deformation and heat treatment will result in control of grain size, the structure of precipitated particles, dislocations, impurities, and the alloying elements in solution. Thanks for watching. Remember to like, comment, and subscribe.